Emisión.
Okay.
Okay.
Yeah. Bueno, gracias a todos por venir al primer JUG del año, and thank Emil for coming from Istanbul and here is proud for us you're here with us. Y nada, recordar que os invitamos a todos a que os animéis a dar una charla, no que tenemos que traer gente de fuera para que la dé. No importa el nivel, sino que lo que importa es, como decimos siempre, compartir los conocimientos que tenemos y compartir nuestras experiencias en la comunidad Java, que somos muchos javeros, pero no nos estamos representados en proporción en la comunidad. Y nada, recordaros que después de la charla nos tomaremos un picoteo y unas cervezas, cortesía de Emisión, y también agradecerles que nos hayan cedido el espacio esta vez. Y que al final de la charla también sortearemos unos códigos de Cognitive para los que estén interesados. And now,
thank you. Hello everyone. My name is Emin Demirci. Thanks for hosting me, and thank all of you for coming to listen to my talk. Today we will talk about stream processing essentials with Hazelcast Chat, and I hope it will be a fruitful, informative session for you. So let's start with who am I? I'm working as an integration lead for Hazelcast Chat product. I'm a computer engineer living in Istanbul. So I'm working for a company called Hazelcast for last 7 years. So this is my whole career. So after graduation, I just start working there. And this will be our agenda today. We will define batch processing, stream processing, and differences between them, when to use it, how to use it. I do have 3 demo applications. I hope they will work while presenting to visualize which kind of problems that you can solve with tools like Hazelcast Chat. So let's start with Hazelcast. Hazelcast is the name of the company. Also, it's an open source company, offers 2 products. First one is Hazelcast IMDG. It's an in-memory data grid. Basically, it is a key value, distributed key value storage. So it has a map API, Java Collections map API, so you can store your data in memory. Hazelcast Chat is today's talk. It is a general purpose distributed stream processing engine. Mainly, and we will dive into that in this talk. So everyone does big data, and there are like a bunch of tools over there, and we have different tools for different problems. So we will just zoom into this area with inside Hazelcast. So this is even from this picture is from 2014. So probably we couldn't be able to fit all the landscape in a single screen anymore. So we'll just zoom into that area. So before our time, the data has been stored in the SQL databases, but different actors with different needs, they were using the same database. Then there is the need for ETL has been risen. The ETL stands for extract, transform, and load. And the main thing is we want to take the raw data and transform in a way that the others can use it. But if we take this to a whole another level, we can run queries on top of it. The main goal is to take the raw data and transform it to an actionable insight. So we are doing this for ages. There's no new thing here, and but as the volume of the data going high and high, we have 2 problems. How we are going to deal with the scale, and also we want our results more faster and more often. So batch processing, in a textbook definition, batch processing is processing previously collected data in a one shot, in a single batch. So it is a linear process. There is no overlap between the stages. So you have to collect the data first to be able to process it. Then you have to process it to be able to use it. So this, by its nature, is a sequential process, and it will induce a huge latency when you want to get the data. So the so benefits or properties of batch processing is you probably run them scheduled in intervals, like hourly, daily, or weekly basis. They run for a specific amount of time. Most common use cases are ETL, offline transaction processing, and data science for exploratory data analysis. So, speaking of the trends, we want to have, as I said, we want to have results more often and faster. And 10 years ago, Hadoop and MapReduce solved the problem with the parallelism and scaling on the batch jobs. You can use cluster of commodity machines to make a distributed and parallel execution for batch jobs. So this was initiated by a paper published by Google. Then Hadoop implemented the MapReduce. Then Hadoop became the most popular one until Spark comes in. But the one thing is, it is working on the disk, and reading from disk is slow process, and then that's a problem, because it was the you have to read the whole data from the disk first. So as the RAM prices, this is even an old chart, but it gives you the trend. As the size in megabytes goes up, the price per megabyte is going down. So RAM is getting cheaper every day, and if you reading data from RAM is like 40 times faster than the reading from disk. And to benefit from this technological advancement, we have to move our data and the processing to the memory, not on the disk. And if you look at the stream processing, real-world data doesn't come in batches. So we want to process the events as they are occurring, not stored in the database for later processing. So we want to know what's happening right now, not what's happened yesterday. Everything around us, these watches, phones, cars, thermostats, generating some data. And even in some cases, data is valuable only for a specific period of time. Think of credit, if you are a credit card payment processor company, you have to decide when your customer swipes your credit card. Within 1 or 2 milliseconds, you have to decide whether you're gonna accept that or reject that. You have to look for the last 2 weeks of transactions. You have to check for location, or utilize some machine learning algorithms to whether validate that transaction or mark it as fraudulent. And the benefits is there is a paradigm shift between them. So batch processing is like a request response model. You make a query and you get a result. But stream processing is event driven. Your system will react to the event near real time. And contrary to batch processing, there is no end of data. You always process. In the batch processing, you read a file from HDFS. When it finishes, your job is finished. But stream processing jobs, usually they are long-lived or runs for infinite amount of time, because you don't know when your data will going to stop. And this is streaming pipelines, how it looks like. And you ingest your data to the system from, could be multiple sources. It could be a Kafka or Pulsar event storage, or you can be reading from database, change stream from database, or your in-memory cache. You do some transformations, enrichment, processing, and you publish your results to the third-party downstream systems. So it can answer queries like these, like a notify if response time 10% over 24-hour average second by second. So it will going to emit results as the events are coming. As I said, there is no request response model compared to other one, and it's also one different thing is it can also leverage multiple data sources rather than working its own data. So you can have like a two stream of events, related events, and you can correlate them together. Speaking of use cases, you can build real-time dashboards that give you some business insights. Change data capture is a hot topic, so there are like tools to listen changes on the database and react to them in real time, like reading the MySQL bean log or taking changes from Oracle DB and using them. Continuous ETL is also another use case. In a traditional ETL, it's a batch process, but you can make it smart and real time. So whenever data comes in, it will be transformed and sent to the store it in a place where it's going to be used. Other thing is a good use case, fraud detection, as I explained in the credit card use case. This could be another. Predictions, and this is an interesting one. You can leverage your existing machine learning models with the stream processing pipelines. So items coming from your stream can be looked up via, you can send the item to the machine learning model, and you can enrich that item with the scoring or classification, or based on your use case, the prediction. IoT on its own, there's like a lot of use cases with the IoT, even on the central processing or edge processing. For example, there are some use cases where it is costing too much to take the data from field to uploading to a cloud, because the amount of data is and the rate of data creation is too high. So you want to process that data on the location. So that's called edge processing. So this it's quite popular on the IoT, and as GuessJet or any other stream processing. Lightweight stream processing engines is a good fit for that scenario too. So let's look at the what are the stream processing engines in the field. Apache's Flink is a stream processing engine. There is a Kinesis from Amazon. There is a IBM Streams, Hazel GuessJet. Spark has a streaming module. At first, it was not a true streaming solution. It was using a methodology called micro batches, so they were emulating the stream processing. But I think in the latest version, I think for the last year or something like that, they created they changed their Spark streaming module to include the true streaming engine. And there's Apache Beam, so it's a technology coming from Google. In 2014, Google launched a service called Google Cloud Data Flow. It was both programming model and the managed service to execute them. And then Google donated this project to the Apache Foundation, and it's named Apache Beam. So it is a unified batch and stream API. So you can, by using the Apache Beam SDK, you can define your stream processing computations, and there is like a multiple Beam runners out there, like Google Cloud Data Flow, the managed service. There's Apache Flink runner, there's Apache Spark runner, Hazelcast Jet runner, and you can run the same pipeline on multiple runners. So it's a good piece of technology. So you don't need to bind with any specific runner, so you can switch between runners. So it deserves a session of its own. So I'll just like drop it as a, if you want to know more, you can go to beam.apache.org to learn more about it. So let's switch our focus to Hazelcast Jet. It's an Apache 2 licensed open source product, single jar with no dependencies. So when you add Hazelcast Jet jar to your project, it won't bring any more dependencies. And it's leveraged Hazelcast IMDG. It's built on top of the Hazelcast IMDG, so it is benefiting from its own production experience. So it's battle hardened for like more than 10 years. So it's built upon that. And it provides a unified batch and streaming API. And if you look at the picture, it's like a more or less same when you put the Hazelcast Jet in there. So you have multiple sources to ingest data from, and Hazelcast Jet on top of the IMDG will run your pipeline, and it will push the data to third-party downstreams. So it provides you a framework to query the data stream and a memory storage to store the results if you want. And why would you be interested to working with Hazelcast Jet? So it is optimized for low latency and then high performance workloads. As I said, it is it's just a 10 megabyte jar file with no dependency. So it gives you data processing, storage, and clustering within a single jar. It has a high level pipeline API. So the API is relatively similar to the Java 8 Streams API. And it has a cloud support, Kubernetes ready. We have Helm charts and discovery mechanism for multiple cloud providers. And let's talk about the concepts. So I keep telling like a pipeline. What is a pipeline? So it is a definition of the computation. So that defines and then links sources, transformations, and then the things and the things. So it's a platform-specific SDK. So for Jet, you need to write your pipelines in Java, and when you write the pipeline, you are using a client to submit that pipeline to the processing engine. when you submit that pipeline to the stream processing engine, it becomes the job. So the job is running instance of a pipeline in this stream processing engine. It runs inside the stream processing engine, and the stream processing engine deals with the code execution, data routing, and flow control. So you don't need to deal with anything. It's responsible for parallel and distributed execution. So when we look at all the building blocks, we define our pipeline with a Java API, and we are submitting that pipeline to the stream processing engine, in our case ASIC-Jet, and it will react to the events from the source, and it will process and publish event to the third-party sinks. Let's talk about imperative and declarative programming models. In imperative programming model, this is a word count example in Java API. So in the imperative programming model, user controls the flow using commands. And let's have a look at the declarative counterpart in the Java Streams API. And in here we are just defining the computation. We are just defining the logic, not the flow. And stream processing engines prefer to have a declarative programming model because it is a higher level code, and it gives us a chance to do some optimizations. So as a user, you define what it needs to be computed, and the stream processing engine make it happen. So you could have think this as a data factory, your pipelines as data factories. So think in terms of what's going in and what's going out. So when you need to figure out what will be your input data in the source, and you have to think about what will be your output, what will be your results. Then it is very easy to come up with the intermediate transforming steps to make that pipeline, to realize that pipeline. So let's look at the APIs. So we will going to see how we can create a pipeline. We'll have a look at the basic transforms, sources and sinks, and I'll show how to submit a pipeline to the cluster. So first things first, you have to add this dependency to your project, and that's all you need to run ASIC-Jet. The latest production version is 3.2.2. We are just about to release a new version called 4.0 version. It comes with a lot of new features. So how we will create a cluster or create a client. So ASIC-Jet has two modes of deployment. First one is the embedded mode, and the second one is a client-server mode. In the embedded mode, when you say jet.new ASIC-Jet instance, this is how you would create a Jet instance. It will create a new cluster member in the JVM that the code is executed. So it becomes part of the application. So when you run multiple instances of same code in a different JVMs, they will discover each other and form a cluster. So this is the convenient way to create cluster in the development environments. Also, if you have a microservice type of deployment, this is this is better suited for those kind of applications. In the client server architecture, you start your Hazelcast Jet servers in a remote location as a separate process, and you are using the same, you are using the client API to talk with the remote cluster. And the returned instance types are the same. Hazelcast handles the client to server communication, so you will use the same API to submit the jobs. You don't need to deal with whether it's a client or server instance. We'll just deal with a single API. Hazelcast will handle the client to server communications transparently. And as I said, Jet clusters grow and shrink dynamically. So if you run one more of this one, the fourth JVM will start and form a cluster. And in the same fashion, if you kill one of them, you'll continue with two modes. So this is a typical code to build and submit a pipeline to the Hazelcast Jet cluster. First, we are getting the Hazelcast Jet handle, and we are creating our pipeline here. We'll see the details later on. Then we are creating a new job, and based on the type of the job, for example, if it's a bad job, we can wait and join to that job to be finished. Then we can shut down the cluster. Or if it's a streaming job, it will run forever, so there's no point of waiting for it to complete. So as we see in the building blocks, we have source, transforms, and sinks, and the API follows the same pattern. So we are creating our pipeline first. That's an empty pipeline, and we start by specifying the source. And in this case, it is a list, in-memory list in Hazelcast. We define our transformations, and we are writing to another list. So speaking of sources and sinks, you start by source definition, and there is no difference between stream jobs or batch jobs in that context. For example, if you put HDFS Hadoop source in here, it will be a batch job, or if you put a Kafka topic, Kafka source in here, it will be a stream job. So the only difference will be the source definition difference, whether it's a stream source or a batch source. Then you keep using the same API for both batch and streaming jobs. Similar to the source definition, you have to define your sink, where you are going to write your results. And those two source and sink classes provide out of the box sources and sinks for Hazelcast data structures, files, Kafka, MongoDB, Redis, Elasticsearch, JMS, InfluxDB. We do have a lot of out-of-the-box sinks, sources and sinks for files, file systems, CSV, and Hadoop files. There are a lot of sources and sinks where you can read from or write to in your pipelines. Let's see a real working pipeline where it connects to a Kafka broker and writes the records to a standard output logger here. So we are using the Kafka sources class. We just define our Kafka properties, bootstrap servers, and serializers, deserializers for the Kafka records. We are defining topic name here, and we are saying that for this pipeline we are not interested in the Kafka record timestamps. We are just going to forward them to the standard output. And if you are familiar with the Java Streams API, those are the same. The mapping phase is like a taking an object and changing its type. Filtering is like a taking, it's like a shrinking the data stream based on the predicate or criteria. You just like saying it applies basic filtering operations. And in the flat map, you take one object and you emit one or more objects. And these are the basic ones. The API, I'm not going to go through all of them, but we'll see what can achievable with those simple basic transformations in a few minutes. And let's talk about enrichment. So imagine you have a stream of streaming data. Before you do any computation to it, you might want to leverage all the data that you know about item to a single object. For example, in this example, you have a stream of trades. You have ticker code, quantity, and price. And also, you do have an external table of company names. So you want to leverage those two to make your computation. So what you are going to do is, this is an in-memory cache, and this is your stream. So you will replace this symbol code with the fully qualified company name. So it's basically enriching the object that you have. One good scenario with that is we can use the same approach to take the item from stream and push it through a machine learning model. And in the next step of the stream, we'll have the item, the score from the machine learning algorithm, and we can continue processing like that. So that could be a good use case of it. And it's also have like two different modes. In this example, in the two examples, the first one is like a in-memory cache. The second one is machine learning algorithm, and you can do it in either a synchronous way or asynchronous way. And you can also, Haskell comes with the facilities to plug any type of service. You can plug any REST API or database, whatever type of system. So you can plug anything in this step. So let's see an actual example. This is our first demo, breast cancer classification. There's a public data set with the breast cancer diagnostics. And in that diagnostics, it contains a lot of information regarding tumors and the size of it, some different properties of it. And there is information whether it's a benign or malignant. And we are taking that data set, and there is a machine learning product or called H2O. Maybe you heard or worked with that. So it provides you a platform to create and train machine learning models, and you can also export models to their specific format called Mojo files, model object optimized. So data scientists will work on that product or any product to create their algorithms and machine learning models. Then you can take that model and plug it in the enrichment step to make it a real-time classification pipeline. So this is the example that we are going to do. Okay, yeah. Okay, yeah. So the source that I'm going to use is the data set is actually a CSV file with around 1,000 records in it. So to emulate a streaming environment, I wrote a processor which takes a random line and publishes to a Kafka topic, and we are going to consume the records from Kafka topic to make it in a streaming fashion. So I'm creating a
I think you have to put the console in the screen.
Okay, then I need to mirror my screen, otherwise. Okay, is it visible to everyone? Okay.
But now I lose your screen with
Okay. So I'm starting the zookeeper, which is required for Kafka. Okay, and now I'm starting the Kafka broker here. Okay, while it is starting, I'm opening up my example application. So this is the producer which takes the, let me show the raw data first. This is how the data looks like. There are like a multiple properties, and this is like a the original data set is like a 570 lines. It's not a big data set. So this is our producer process, which produce lines to the Kafka topic called diagnostics. So it's producing one event per second. So it is for convenience to follow them on the command line. Like we can produce at a higher rate. And the actual code for the computation is here. Come on. Why this is coming up? I can't go into presentation mode.
I had this issue before and I fixed it, but I don't remember how.
Okay, yeah. So we are creating our jet instance here. In the job configuration, Hazelcast Jet has an ability to attach some resources along with the job that you can reference that while inside your pipelines. So you can attach domain classes, or you can attach reference files, lookup tables. In this example, we are uploading the model which has been produced by H2O. So this is a zip file. We are uploading it along with the job. So later on, we will unpack it and load it in the JVM. Then we will do some method invocation in that model along with our objects from Kafka topic. So we are uploading that file with the job configuration. And in the pipeline, this is our whole pipeline. Similar to the one that I showed, we are reading from Kafka with some Kafka properties like serializers, servers, and the address of the servers. And we are, since it's a CSV line, each record, so we are mapping it to a POJO. In here, we are parsing the CSV to a plain old Java object. And from there, we do have stream of POJOs, but we are not using the how to phrase it. Then we have objects in the stream. Then we are going to apply machine learning classification to whether it's a benign or malignant. To achieve that, we have to load the machine learning model that we uploaded with the file. So this method is creating a context object from the model file that we are getting here. So this is our zip file, and this is a class from the H2O product. So we are loading that machine learning model, and we are going to use this context here to make a prediction. So we are taking the in the pipeline, we are using a map using service, which means that I'm going to do a mapping with a custom service object that I created. In our case, it's the machine learning model from that file. And this is the definition for that context object. And in the second lambda, the first one is the context object that we passed in, and the second object is the actual object that coming from Kafka. And what we are doing is we are getting the data as raw and make a binomial prediction, and it returns a response. And we are interested in the label of that response. and we are comparing that response with the actual data from the data set to see whether it's a match or a miss. So we trained our machine learning model to, without looking at the output, it learned how to differentiate between benign and malignant tumors, and we are comparing its performance here. And after that, we are just writing those results to the logger. So let me run this application. So let's go back. So it created a single node Haskell cluster here, and this is the our job definition. So we submitted our job to the cluster, and then it started processing the events one by one. And if we just go down, it is processing one event per second. So if we look at a single one, it says it's in the original data set, the tumor is a benign one, and the prediction is benign, and this is the like the scores for each label. So this one is like I don't know, 3 times higher. So it's actually made it matches with the original data. So it's similar. Let's see if there are any miss ones. Yeah, in reality you will have like you never have like 100% correct machine learning model, but since the data set is very small and the features of the data is like unique, so it has a very high correctness rate. So yeah, this is the first example. Let's see. Let's continue. I just can't bring back the keynote again. Okay. Now I think I need to This is so hard. Right? Yeah. Okay. So yeah, we've seen the mapping and the map using service. Now have a look at the aggregations API. We have rolling aggregation, windowed aggregation. So the aggregations are typical operations like summing up values, calculating averages, finding minimum or maximum values, which you are familiar with from other tools. So what they do is they are combining multiple records to a single one, and they are like typical examples of stateful processing. And so the rolling aggregation will keep the value and then emit a new value. Let's go from the example. So rolling aggregations can answer questions like tell me the maximum temperature seen in this room so far. So for each record, it will tell you the maximum temperature. So if it's a higher one, it will emit the highest one, but it will emit whenever an item comes in from the stream, it will emit a one value. Windowed aggregations are again like typical summing, averaging aggregations, but they bounded with a scope. So scope is a window, and we'll see the definitions and the types of windows later on. So we have to bound the data in a stream processing engines, because it is like a fundamentally different than batch processing, because both input and the output is continuous. So you have to deal with some notion of time. You have to you are interested in how the value changes over time. So the typical way to solve this problem is look the data in terms of windows, which represents a slice of the stream, and it is constrained by the time. So, for example, if you say, if you try to get the results since the app started, so it's like a potentially infinite. But if you just say, give me the result for the last 30 seconds, you're defining a window. So how you are going to get the results? It's also a problem you have to think about. You want results for each item, or after you process all the items in the scope, or for example, you can say you can specify some specific intervals, like give me count of tweets in the last 1 minute regarding topic X, but you want to get, you can either wait for 1 minute to get the count. This is normally what you want, but in some use cases, to take an early action, you also want, okay, even though it's not an approximate or correct answer, you get me, you publish a result every 5 seconds. So this is called early window results. So let's have a look at the type of windows. There are three types of windows. Tumbling windows is like equal sized windows. They are windows in series. So if you think like this is like a 1 minute window, you get the from 0 to 1 is like a one window, from 1 to 2 is another window. Sliding windows is similar to the tumbling windows. The window is equal sized, but they are sliding by a step size. So, for example, give me an example query would be, give me the number of tweets regarding Valencia JUG for last minute every 5 seconds. So this will be our 1 minute window, but we'll slide this window every 5 seconds. So every 5 seconds we'll have an information regarding last 1 minute. So most of them, like each window will be overlapping to each other. And we also have session windows, which can represent user activities, like start a session when user signs in to your website, as long as user keep doing activities. You keep the window open. You define some timeout value. If there is no activity, say for 30 seconds, you close the window and you process the events within that window. And let's have a look at the event time processing. Normally, or in most of the systems, events arrive to the stream processing engine out of order. So when dealing with out of order data, users can simply timestamp events as they arrive. So this is called processing time semantics. Or you can use the timestamps from the event inside the record. So in terms of Kafka, for example, you have timestamp assigned to each record. So you can use that to as a timestamp in the stream. So in both cases, timestamp used to assign events to the windows. So as the items can arrive out of order, we need to define how long or how much latency that we are allowing within the system. For example, say there is a 10-second windows in your system, and events are coming in unordered fashion. So how long you are going to wait for the late events. So the longer you wait, the more correct results you are getting. But you can't wait infinitely to have like 100% correct results. So there is a trade-off between the accuracy and the latency, because if you wait, for example, say 1 minute to get this 10-second window results, you have to wait whole another 1 minute to make it more correct. So it depends on the use case, but sometimes you need to say, okay, if event doesn't come in for say like a 10 seconds, I'm not interested in that, or you can take a special action to reprocess that event later. So it's a trade-off between the correctness and the latency. And Hazelcast Jet takes a simple approach, so you can configure this latency setting, and as we have discussed in the trade-off. So I do have 2 more demos that I'm going to show, and let's see how we can build a simple dashboard with Hazelcast Jet. So I'm still I will try to make it smoother because I got experience right now. So I will make it mirrored. I'm going to present my screen. Yes, this one. And now I will so similar to the other example, this one is there is a event generator that generates random events random trade events to simulate a trading environment to a Kafka topic. There will be a Hezekiah pipeline which takes those events and calculates three different aggregations. One is the count, how many events, how many trades occurred for that particular ticker, the volume, how much money got into that trade, and the latest value of that stock. And we are built a web dashboard that shows these information for all these tickers with a capability of drilling down of each one. And we are, let me run this trade producer first. This will publish events to the Kafka topic. And this is the aggregate. This is the actual. Okay, yeah, I need to start server first. Has a guest yet? So the aggregate query is the actual query. Load symbols. It is taking the symbol names, and it has the ticker code to the full company names. We are going to use it while we are presenting on the web page. So that one does that job. And run the aggregate query. And finally run the web application. So let's examine the pipeline. So similar to the ones we've seen before, we are consuming events from Kafka. We are just interested in the Kafka consumer record value with the topic, and then we are we'll do a rolling aggregate, and we are doing this rolling aggregate for with a grouping key of symbol name. So by doing that, we'll have results for each symbol. So for each symbol, we will have these three aggregations. First one is just counts how many events that goes into to aggregation. Second one is we are going to product price with the quantity, and we are going to sum all of them to calculate the volume. And in the last one, we are just returning the latest price, and we are writing them to the Hezekiah IMAP, which is a in-memory distributed cache. And if we just look at the web application.
But after you are computing three different stacks, you are going to have a list or something like that? Or?
Yes, that's going to emit three different, one object with three different, three different properties. Yeah.
Okay.
So, yes, this is the application. This web server, this front end will communicate to the back end via WebSockets, and initially it will poll the whole list of events. Then after initial snapshot, it will just listen for changes on the IMAP with a IMAP listener. So in initial it will do a big load, then we'll just seeing these updates coming from IMF via listeners. So as we are seeing, we have the symbol name with a full qualified name coming from the enrichment, and we are seeing the price. And if we just click on one of them, we are seeing the raw events here. So for example, this has like a 415 records. This is the count aggregation coming from there, and this is the latest value aggregation, and you can see the volume is here. It's like a $54 million. So yeah, and you can also see all the individual events happened for this trade here. So this is an with having a 10 line pipeline, you can like a back. Okay, yeah, there's a lot of code on the front end to make it like a. You have like you are going to write more CSS code than Java code to make this happen. Because these ones we spend more time on that. But yeah, you can create a real-time dashboard with relatively small effort from compared to front end. Yeah, let's stop this example and so I'm going to stop Kafka and the Zookeeper. This way it will be more easy for me. And yeah, I'll show one more example, which is flight telemetry one. So let's open that up. I don't know if you are following the hacker news. Yesterday there was a ADSBexchange.com which made it to the hacker news front page. That is so each airplane on the air emitting some messages on a special frequency called 190 megahertz. So if you have a special software defined radio with a small antenna like this, you can listen for those messages, and those messages include where the airplane is, in terms of GPS locations, its body type, its heading. It contains a lot of information, like and it is free, and there is no since it's one way, you can listen for it, and there is no legal issues with that, listening to it. But when you have that antenna, you can only see with a small antenna. You can only, if the airplane just passing over you, you can only see one or two airplanes with a small antenna. If you install a bigger one, yeah, you can increase your perimeter. And there's a community website called ADSB Exchange. Normally, if you are familiar with the flightradar24.com, this is also using the same messages to show the flight information. And there's a community website called adsbexchange.com. So they provide you the infrastructure. So you install your antenna, and you are sending that data to adsbexchange.com. And the beauty of it is everyone around the world installing their antennas, and the coverage around the world is compared to the real time. Every individual collecting data is from its neighborhood. For example, we do have one antenna in our Istanbul office, and we are sharing data from Istanbul to that community website. And when you are sharing this data, they give you a key, and they give you access to the whole information. So this example is. Oh, sorry. I'm not supposed to show that key. Maybe we can cut that because that's our key. Anyway, you can like the antenna for making those publication is like a $5 to $10, maybe a similar value in euros. So you can install on your own and look around the data. So what we are going to do with that data, we are going to we specified 6 airports, and we want to calculate how many flights are landed at that airport or take off from that airport in real time. Also, we are calculating 2 different metrics. First one is carbon dioxide emission around that airport, and the other one is how much noise in the near to the airport in the, like a 16-kilometer perimeter. So how do we calculate those information? First, there are 2 tabular data. Aircraft providers providing carbon dioxide emission values for each body type. So we know that how much carbon dioxide Boeing 777 emits in a single takeoff. Similar to that, we also know that how much noise it generates in a specific parameter. So by utilizing this information, we can calculate some metrics and compare it cities with those information. And also, it is known that flights have multiple phases: initial takeoff and landing phases. And by looking at their altitude information, we are, for example, we are filtering out cruising airplanes above 10,000 kilometers, and we are only interested in the landing phase or taking off phase. And we are calculating linear trend of the altitude information that gives us whether the airplane is going up or going down by looking at the coefficient. If it's a positive, we can say, okay, yeah, the altitude is increasing, is taking off. And by utilizing all of these information, we are pushing that data to Graphite database, and we making a dashboard, Grafana dashboard. And yeah, let's run the demo. So this will just bring up the Graphite, Grafana, and those Docker images. And now we are going to run flight telemetry application. Well, this is relatively complex to the examples that we see, but you can still follow it. So there is a flight data source which I leaked the API key. We are calling a specific endpoint with the key, and it will return the whole information about the aircrafts that they have. We are using timestamps from that source. We are filtering out the grounded airplanes. We are not interested in them. Also, we are looking at the airplanes between the altitude of 0 and 3,000 feet. That's where we're interested in them. By looking at the latitude and longitude information, we can say that, okay, whether this is near to the, for example, Valencia airport or not. So we are mapping the airport name to the object, and we have a sliding window of 1 second, 1 minute. We are going to have results for grouping key for each aircraft, and this is the aggregate operation where we calculate the linear trend calculated based on the altitude value, and by looking at the coefficient we are assigning it the vertical direction is going up or down, and from now on we are branching and writing landing descending flights to one IMAP and taking off flights to another IMAP by just looking at their ascending or descending information. And here we are, let's make it full screen. Here we are enriching with the noise information, and this is the CO2 information. How we are getting them is from the method. There is a lookup table, and it is filled with the, some data from, this is like a static data. We just like referencing that by body type, and we are getting values from there based on the body type. And we are writing those values to the graphite sink. So we are sending all the data to the graphite sink, the carbon dioxide, max noise, landing and taking off flights. And so okay, so let's run the application first. So flight telemetry. Okay, we pulled 10,000 aircraft information, you know, which is okay. Now we have the data. So yeah, that yields a dashboard like this. We can see carbon dioxide emissions for the 6 airports. Currently, New York is the busiest one, or like a. And this is like fed by the real-time data. For example, right now, like from the start of the demo to this point, 4 planes landed to Frankfurt or Atlanta or New York. So let's verify whether this is like a fake data or real one. So yeah, let's take this one. Says new aircraft landing. This is the registration, and it's landed to London. Let's cross-check with Flight Radar 24. Fingers crossed.
I think if you are not a premium user, you can share the
No, you can still see. Okay, yeah, it is approaching to land to the London from Glasgow. Yeah, it is in 4 minutes it will be landed. And we catch this with like a public information with our pipeline. And we can have a look at another one. Maybe this one is taking off from Frankfurt, A320. And yeah, it's not Frankfurt, it's Cologne, but maybe there's a, I don't know why it's said it's still in Germany. It's like but yeah, it just took off and going to Vienna, you know. Yeah, you can, like, there's multiple of them, and maybe one from America, New York, Atlanta, this one. Yeah, it just took off from Atlanta. It's going to Chicago. Yeah. So yeah, with maybe 200 lines of code and a small antenna sharing your data with flight, the ADSB exchange, so you can build a real-time dashboard like this by utilizing Hazelcast Jet. And yeah, you know, the data, this is like the compelling data set, but in your, we are not like every time, we are not so lucky to work with this kind of data. But still, Hazelcast Jet is like a piece of technology that could be a valuable asset in your skill set, because it's with a simple pipeline API you can build real-time systems. And let me close the demo and wrap up my presentation. Oh, also, if I haven't showed the management center. So let's run this again. So we can also see the noise levels. And this is the management center tool from Hazelcast for monitoring and then diagnosing your pipelines. So from now here you can see information regarding your cluster. You can see the jobs, failed jobs. You can see detailed information regarding your individual members. The interesting part is when you click on the job, you'll see detailed metrics and the directed acyclic graph view your pipeline, which I will talk in a few minutes. But you can see right now we processed like a 24K records in, and you can see drill down into individual steps, like how many records each step processed, or how many processors you have, the latencies, stuff like that. This is helpful while you are developing your applications, because if you made a mistake or something like that, for example, your stream pipeline doesn't producing any output, and normally it's hard to debug without kind of tool, because you have to guess which stage the output is not emitting. You try to put log lines over there and redeploy your job. But with a tool like this, you can immediately spot that, okay, yeah, this stage doesn't have any outputs. Then you can identify your problem. So this is helpful for debugging. Also, you can also manage your job. For example, I can suspend my job, take the snapshot of the job, upgrade the job definition, and like resume the job where it left off. Stuff like that can be done with this management tool. So let's close this job. And okay, yeah, we also seeing this DSP processing. So how this is working, what's the underlying technology to make Hazelcast happen? So directed acyclic graphs are used to model computations. So you have a one-way graph, and the vertices are representing your processing steps, and the edges between them defines the data flow between them. So when you define your pipeline, Hazelcast takes it and transforms it to a directly acyclic graph and runs that graph on all the members. So it's a generalization of MapReduce paradigm. In the MapReduce paradigm, it's like a linear process. You have to think in map and reduce steps to represent your computation. So it says it limits your ability to express your job. It's hard to think, in map and reduce steps. So, but this one is like easier to reason about and has more usage. So supports batch and stream processing and other systems like Apache Test, Flink, Spark, Storm. Most of the tools out there internally uses this directed acyclic graph approach. Hazelcast also exposes a low-level API where you can write graph definitions with the low-level API. We are not suggesting them to use it if you are not knowing what you are going to build, but if you are a library developer, so you can build anything. So we're providing a directed acyclic graph definition and execution engine if you are interested. But it's like a way more hard than because you have to define each processor and you have to wire in each vertices in the correct ordinals and stuff like that. So it gets complex pretty easily. But in the pipeline API, we do it for you. You just define your pipeline, it gets converted to the directed acyclic graph and executed on the Symbios engine. And yeah, in the this is again the word count example. It's just a linear one because you'll just do a series of events. But this execution plan gets created and executed in parallel on the cluster of Hazelcast machines. So the parallelism, all the stuff has been handled by Hazelcast automatically. You don't need to deal with data partitioning and other stuff. All you need to do is, for example, say that, okay, run this map step with 16 instances, stuff like that. You just need to define the parallelism. Other stuff has been handled by Hazelcast. So to recap, what distribute means to Hazelcast, there is you can run in multiple nodes. They are elastic. You can add any new nodes on runtime. Data is stored, partitioned, and then replicated for a recovery. For example, if you just keep only one replica, if you just lose that replica, your data has been lost. So that's why you replicate your data. And there is no single point of failure. So when you have multiple replicas, if one of them goes down, you can still recover your data. And this is the more realistic view of that word count example. So you have 2 nodes, and you send that execution plan to both nodes, and even in each node you have like a parallelism, and this like a accumulation or group by steps has been handled by Hezkechat, and this is how the underlying engine executes the pipeline. So speaking of product roadmap, on the connector side, these are the ones which is available right now, but also with the new version, we are working on Apache Pulsar. With the new version, we are about to release Kafka Connect and the Debezium one with 4.0. 4.1, we are aiming to release Pulsar one. On DevOps side, right now we are working on integration with enterprise PaaS, and we are also working on Kubernetes operator that we have. We already have like a Kubernetes integration and Helm charts, but we are working on operations framework. On the streaming side, with 4.0, you can plug your Python functions in it. So we are giving you ability to create a Python process and run arbitrary Python functions from the Jet pipeline. So that's also coming with 4.0. With the 4.1, we are starting to work on SQL research. So how we are working on how we are going to provide SQL support for pipeline definitions. And yeah, these are the all the demos that you see is source codes available on this repository. Jet.hazelcast.org is the project website. This reference card is contains bite-sized information regarding stream processing. We are active on this Gitter room, so if you join, you'll have an access to all the Jet developers we have, and we are active on that. Also, if you have any questions, you can post to the Google group, or if you tag with the Hazelcast Jet tag on the Stack Overflow, we are constantly monitoring that place. Thank you. I hope you like it, and if you have any questions, please speak up. We are also hiring, so if you're interested. Yeah.
Question for you is the Hazelcast Jet Manager is also open source?
It is not open source. It is free up to 2 nodes, I believe. So if you have a bigger cluster than 2 nodes, it goes into enterprise edition. But for the Hazelcast Jet, it's all open source, so you can create as big clusters as you'd like. But yeah, for up to 2 nodes, it is free. But if you have a bigger cluster, yes, that requires a license key. But you can apply for a license key that give you like a 30-day free trial. So, or if you have a development cluster, you can have a look at that up to 2 nodes.
Okay.
I was going to ask if the management Jet application is included in the jar file.
No, it's a separate jar file. We are packaging them separately, so you can download it from the website.
No, because I was wondering if it's amazing that you can package everything into a package.
Yeah, but since it includes JavaScript files, it's like a front end and stuff. It's not 10 megabytes. I don't know how big the management center application is. It's around 50 to 100 megabytes. I'm not sure, but the Jet should be around. I don't know. I don't want to be like it's no bigger than maybe 50 megabytes. Let's say to be on the safe side. Yeah, it's a single jar file without any dependencies. So yeah. More questions?
It's more technical question. So you said that you have kind of replicas for avoiding losing data, but if you have any checkpointing mechanism to ensure that you have delivery guarantees?
Yes. I completely forgot that in the presentation.
Okay.
Yeah, we do have a checkpoint mechanisms also with the processing guarantees. So you can configure at least once and exactly once processing guarantees, and you also can Hazelcast Jet will take the snapshots to Hazelcast IMAPs. So it's an in-memory solution, and you can define the interval, like say every 5 seconds you can initiate this like a snapshot process based on the how big your objects that will go into the snapshots. And in the enterprise edition you can also make that in-memory snapshot storage persisted to the disk. And yeah, we are providing at least once and exactly once processing guarantees based on the source and the things that you have. Like if your source is like a rewindable, and if your sync is idempotent, you can have exactly once delivery guarantees. But other than that, it's not possible, because like when you push an item to the downstream, you cannot just take it back. So it depends on your source and sinks. We also have some transactional sources and sinks. So yeah, if like say JMS or JDBC, so you can take in. I didn't want to go into details on introduction level, but yeah, it's good that you asked.
This is some issue, not with Hazelcast, with Flake and Kafka. So that's the question. So you need, to have exactly once, you need the Hazelcast in memory as well together.
Yes, because you need to
both parts.
Yeah.
To achieve this.
Yeah, but it comes out of the box. When you are defining a job, there is a job